magnetic. It's a fine suspension of iron particles that we can control with a magnet. So if you look at it, you can even see the lines of magnetic force in the surface of the liquid. So I'm going to pass these around. You really can't see much until you get it. One thing I will warn everyone, first of all, be careful with the flasks. They are glass. And although the liquid inside is not toxic, it is disgusting. And so if you break the flask and you get it on you or on the table or on the floor, it's never going to come clean. The other thing I will tell you is resist the temptation to take the magnet and use it to paint the glass, because the liquid doesn't float off the surface of the glass very well. Once it's painted, you can't see inside. So keep the liquid at the bottom, and you can move that around. Here, I'm going to send something down the center. I didn't send anything that way before. So you can take the magnet and move the liquid around inside. All right. And then it may be too hot in here for us to even use these. Another interesting modern material, liquid crystals that are temperature sensitive. Each of these things is a liquid crystal sheet, although we may have gone beyond its transition temperature in this room today. You can put your hand on it and you can actually see thermally where your hand has been. We'll send a couple of things there, but like I said, we may be over the temperature limit on those things today. There we go. Now everybody's got something to play with, so that you don't have to listen to me. But we're going to talk anyway. So we're going to talk a little bit now about solution chemistry. That is, chemistry taking place in a solvent. Everyone here is familiar with solutions. Everyone's made a solution at some point in your life. Think back to when you were a child, if you're an adult. You must have made Kool-Aid at some point. What is Kool-Aid? Kool-Aid is water with sugar dissolved in it. Everyone's made Kool-Aid, you know, and I'm sure that when you were young, you thought to yourself, gee, if 1 cup of sugar is good, 2 cups of sugar should be better. What happens if you try to add that 2nd cup of sugar to your quart of Kool-Aid that mixed? It sits there on the bottom. You make what's called a saturated solution. Well, I have a chemical here called sodium acetate. Sodium acetate is not very bright as far as chemicals go. It's easily fooled. It's easily tricked. So dissolved in the water here, I've actually dissolved more sodium acetate than should theoretically be able to dissolve. I've gone beyond its saturation point. It's what's called a supersaturated solution. Just how much solid is dissolved in how much water can be illustrated by taking a single crystal, a tiny crystal of the sodium acetate material. And now I'm going to dump this out. I'm going to dump out my supersaturated solution onto the crystal. And you can see that the solids dissolved in the water begin to crystallize out. And they crystallize out to such a degree that the water ends up being completely entrapped inside the solid. That if I pour slowly, I can actually grow a column of crystalline sodium acetate. Now, unfortunately, I can't talk in pour very well. I don't know how high I can go. I'm going to have to quit soon. Eventually, it's going to tip over on me. Should I keep going? You want to see it fall? Okay. Now, to show you this process a little differently, it only takes one crystal of the solid material to get the started. A single crystal dropped into the flask. And you see the solids begin to crystallize out of my super saturated solution. And as they crystallize out, the water ends up being trapped inside the crystal structure. So that essentially there's no free water. What's interesting about this, if you feel the bottom, what can you tell me about it? It's warm. You feel the bottom, it's warm. Energy is released in this process. This is the basis of an ordinary home product that you can buy down at the sporting goods store. Any backpackers, snowmobilers, outdoors people here that know where you can get this same chemistry? Reusable hand warmers use this exact same chemical process. To put this back in the solution, I'm simply going to take it down and heat it up on a hot plate or throw it in a microwave oven. When it warms up, the solids will dissolve, but they don't know enough to undissolve as they cool back down. When you bend the little metallic sheet inside your hand warmers, it causes the crystallization, and you get the crystallization, which also releases heat. So these are reusable. I'm going to use this over and over again for the next however many shows I do. All we have to do, throw it back in the flask, heat it up, and we will have our super saturated. Okay, let's talk a little bit more about combustion. You seem to like combustion. So this is just a spare. In case we screw that one out. Let's talk a little bit more about combustion. Here I have some phosphorus. Phosphorus is another material that burns. But we were talking a minute ago, in order to burn, what does it need? It needs oxygen. And the air in the room contains oxygen, but it's only about 20% oxygen. So, although I can light my phosphorus and it will burn, my phosphorus will burn in air. It will burn quite a bit differently if I give it more oxygen. Here I have a flask. In this flask is oxygen gas. Let's prove to ourselves first. Let's prove to us phosphorus burns. We can see that. But if I put it in a container of oxygen, it burns quite a bit differently. I call this the glowing orb of chemistry. This is how I gaze into it to determine my student grades, you know. I'm sure that's how your teachers do it as well, you know. Inside this flask, we have oxygen and phosphorus that are burning to form phosphorus pentoxide. This reaction can only go until one of the two materials gets used up, and then it has to stop. That's what we call a limiting reagent reaction in chemistry. As soon as one of the two materials is done, the reaction has to quit. We can't continue to go. So inside now, there's a white smoke of phosphorus pentoxide. Phosphorus pentoxide, somebody told me to safety class. Phosphorus pentoxide inside the flask. So that's an example of combustion in a closed system.